and make something that's much better. And so this is an area that started out as a collaboration between a group of people, a company called Cargill, which is a US company that has corn and soybeans, the Department of Energy in the US, Material, which is a small company in Pasadena, which is another company I helped found, which is commercializing this technology. And the interest in this was that they wanted to replace petroleum-based products with those from renewable resources. And corn oils and oils contain this special unit, which we work on, which are two bonds between carbon. And that's what makes them oils. And so this was successful enough so that it resulted in a company which is called Elevance, which is now moving forward. And one of the things that they've just announced is and so this is the kind of chemistry, so this is just making and breaking double bonds and making pieces and putting it together. And the part that is important is on the next slide, is that you can modify these oils to make them into things that will can be very useful. And so the kinds of things we do are we take soybean oil, which you see has a double bond in it, and that can be hydrogenated to make cooking oils, or you can hydrogenate it and make waxes. And so they're selling this stuff they call nature wax now. But they found it didn't work so well, but it worked much better if they put in our catalyst and changed it before they hydrogenated it. So this leads to a whole bunch of products, but the exciting thing is just the announcement of recently that there's now going to be a very large company that's being formed, which is associated with this chemistry. It's going to happen in Indonesia, and the whole game is, if you looked at a refinery that now takes place, you would find a situation where you take a barrel of oil, you put it into some kind of treatment, you do some chemistry, and then you distill. What they plan to do is to start with seed oil as a source of carbon instead of petroleum, do some chemistry, and the chemistry they're going to do is the chemistry which was developed at Caltech, which is metathesis chemistry. And this will happen in a moment. Here we go. And so that's our catalyst, which we made at Caltech, which will go into this very large plant. Then they will distill, and out will come products ranging from, it's a little hard to see, so jet fuel, green fuels, various lubricating oils, etc. So just as now one puts in a barrel of oil and makes a variety of chemical products and fuels, this will start with seed oils as a carbon source and turn it into final products. So this is very exciting for someone who started out studying this chemistry just because it was fun, just because it was an intellectual challenge. Now to see it start to move into a much larger operation has made it extremely interesting and a lot of fun. So that's my normal life. That's the life I lead most of the time at Caltech, working with graduate students and postdocs. But there's another life which I found very exciting over the last number of years, starting quite some time ago now, which started a kind of collaboration which I think is going to be essential for us to move forward in many areas. And this is in the area of trying to develop new clinical treatments. There's an incredible amount of new science taking place. There's an incredible number of new problems that are arising from clinicians and in the medical world. And the question is, how do you get them together? And how do you get people talking? How do you make the right matches? And so I was lucky. In about 1975-76, Dan Swartz, who is an ophthalmologist at UCSF, came to Caltech. And he said, here's a bunch of problems that we have in ophthalmology, which I think basic science and material science could help solve. Now the key to this was Dan understood the problems and was able to define it precisely so that a chemist could understand it and start to think about it. And one of the problems he put forward led to the light adjustable lens, which Dr. Chayet talked about a little earlier. And I'll tell you a little more about the story. And so why do you need this? It turns out that it's an incredibly common surgery. It happens many, many times. But the key that Dan recognized was that nearly half of cataract patients require spectacles after the surgery. And if you have astigmatism, it's always, and you still need glasses to read, even if you have good distance vision. And so there's a variety of problems associated with getting exactly the right power. And then also the problem is associated with how the wound heals after surgery. And so it's a problem associated with trying to get everything right. So in the present day, when people want to have spectacle-free vision, one would like to be able to continue with this after one has this kind of surgery. So for me as a scientist, this was a real challenge. So how do you make a material that you can implant in the eye and have all the right properties to be a lens? Then 2 weeks later, after everything is healed, you can go back and externally change the refractive power. And that's a really interesting problem. So for me as a material scientist, this required us to develop new science and new technology, which is really what it's all about. So here's the sort of deal is that, basically one wants to have spectacle-free vision. And so the question then is, can we develop the right kind of material? One more time, here we go. Here we go. So, and so this is the next part of the problem, is that you put together a team of people who can work on this project. And so Dan came in, he produced the problem. He was a clinician. This provided the challenge for the scientists to be able to come up with a concept. And fortunately, I was able to come up with an idea about how to start solving this problem, which turned out to be not so far away from how we're doing it now. We needed a lot of help on this, and so Julie Cornfield is a material scientist at Caltech. She's an engineer. She knows how to study materials. And then we recruited a postdoc, 2 postdocs, Chris Stanstead, who's still with the company and a really key person, and Yagdish. And so they basically then were the people working with me who developed the initial concepts and demonstrated that we could make a material that you could adjust with light from a distance. So that was the first thing. But that's a long, long way from having something that's useful. And that's about all the scientists can do if they're working by themselves. So the next question then is how do you turn it into something to make it work? So what you need then is a material that looks exactly like the present material. You're able to make the proper changes, and it has to have all the mechanical properties and all the features that are required. So so working together, we were able to develop the proof of concept. We then started a company so we could develop it further. The next thing, working with Dan and his connections, we demonstrated this in animal models, in rabbits, and it worked really well in rabbits. Turns out that young rabbits have perfect eyes. They're all the same. They don't complain. So it was really easy to get the concept there. So a company was formed based on all of this work, and things move forward. And so what's the idea? And so Dr. Chayet showed some of this. This is for the chemist. But basically, an intraocular lens is a plastic, a really big molecule that's connected together, and it makes a mechanical shape. And that's what is put in people's eyes now. What we do is we add something we call a macromer, which is a smaller molecule, which is here. It's hard to, where's my laser? Here we go. It's hard to see on this, but basically it's these small red molecules. And they have things at the ends which are sensitive to light. And so when you shine light on these, they react and they couple up with other partners. So that take small molecules and make them into great big molecules. And that's really the whole trick. And so then what we can do then is we can make these things hook up in special places. So what we do then is, if we want to increase the power of the lens, is we just remember there's a hole here now. Is we just shine light in the middle, and so that takes the reds and turns it into blues. So that's these bigger molecules. Once they're really big, they can't move. So they're small molecules, they can move around. Really big molecules, they can't move. And so these really big molecules can't move, and so they stay in place, but the little molecules then see that they're lacking partners over there, and so they move into the region where we polymerize the material. So it goes from pink to blue, and then we got the blue, and now more pink moves in. So you see there's no pink there, and now there's pink. So when this pink stuff moves in, that causes that to swell. So that part of the lens will swell, and the other part will shrink, and so that then causes the power of the lens to change. And so we can do this now by putting a pattern of light onto the lens through the pupil so that this works. And then the last part of it is once you have a lens exactly the way you want it, light's going to be shining on it all the time. So how do you keep it from happening? So then you just shine light on everything, and then all the pinks turn into blue, and then it's stopped. So after you put in the second set of light, then you're locked in, and everything is permanent. And so now there have been lenses in. How many years have these lenses been in, Dr. Chayet? Yeah, patients, yeah. 7 years, yeah. And they don't change after that. So this lock-in procedure works. So this is the way, the idea we conceived of it originally was this idea of polymerizing in a region and causing things to migrate. We were lucky, it works even better than we had planned. Sometimes that happens in science. But it basically works that way. But it's a long way. I told you this was 1995. Here it's 2010. So it's taken a long time to go from this simple idea to the final product. And so what you want to do then is to put on patterns of light so that you can cause different parts of the lens to change. So you can shine light on the outside, which makes it flatten. You can shine light in the middle, which makes it expand. Or you can put things on an uneven pattern so you can correct astigmatism. So we started a company, and it's moving forward. Lots of things have been implanted. So basically it's a standard. If you saw a standard intraocular lens, it would look exactly like this. They go in exactly the same way, I understand, and so it was easy to design. So the next question then is, how do you make this work, and how do you put on these patterns of light? Here we go. Oops. Now we got to go back. Because the important picture is the one we skipped over, which was the third piece of the puzzle. Is that you need the clinician to make the original problem, and then you need the, I got two T's in there, sorry. I did that the last minute.